Okay, on the next set, check the answers, and we got 20 out of 20 so far. Woohoo! Apart from I forgot to actually circle one of the answers. I thought I ticked it right. So I might have lost a point for forgetting to circle it, but hey-de-ho. So we're on the next bit, so we're sticking with rates. So question 21, data shows the effect of change in reactor concentration of the rate of the following reaction. Fluorine reacting with this chlorine oxide to form this unfamiliar substance. So here we got our concentrations, and then we've got to find the order with respect to fluorine and the overall order as well. So the overall order, once we take into account the effect of this stuff as well. So let's look at sort of first of all what's going on. So here we keep the concentration of fluorine the same, but we treble the concentration of the chlorine species, and we can see that the rate is 3 times faster. So that means that it's first order with respect to this stuff. Because if it was second order, then that would be 9 times faster, because it would be 3 squared. And if it was 0 order, then it wouldn't have any effect on the rate. So the fact it's directly proportional, we treble it, that trebles is first order. So then we've got to consider, okay, what's the order with respect to the fluorine itself? So here we keep the concentration of chlorine species the same. So that, and then in this one we increase the concentration by sort of 50%, so it's like a half, 1.5 times, so 1.5 times that, and then 1.5 times 1.2 is 1.8, so again it's first order, so we increase that by 1.5, that increased by 1.5, so it's first order with respect to the fluorine as well. So that means that it's first order with respect to fluorine, but it's second order overall, because it's 1 plus 1 would be overall order of 2, so we're going to go with D. Marking with red pen, let's go back to black. 22 is some rates graphs, so again you want to be familiar with these. To be honest, I haven't really come across this sort of shape graph before, so I'm not really sure what's going on there. And then in this one we see that it's rate against concentration. This could be a second order one looking at that. If it was second order, a good way to kind of show that would be to plot rate against the concentration of the reactant squared, in which case then it would become directly proportional if it was second order. Looking at this next one, this one always stands out like a sore thumb. That's 0 order, whereas this is not. That's going to be either first or second order. Sometimes you can tell from the sort of the rough shape of the curve. I'm not so good at that myself. Obviously, you could measure half-lives if there was a scale to it, but whatever happens, that's 0 order, and this isn't. It's either first or second. This one, that's 0 order, and this one is 0 order. That's where basically the concentration of the reactant has no effect on the rate. So as the concentration of the reactant changes, there's no effect on the rate. We just get this kind of complete linear sort of decrease in the concentration of the reactant. So I would be going with C. Again, this is 0 order. This one here, that would be first order. So when you get that directly proportional relationship going through the, what do you call it, origin, then that's first order. So it's not going to be that one. Okay, 23, which of the terms in the Arrhenius equation takes into account the orientation of the molecules? A is the Arrhenius constant, and that's the one, so it's the Arrhenius constant. EA is the activation energy itself, R is the gas constant, and T is the temperature. What is the effective increase in temperature on the equilibrium? So if we look at it, delta H is negative, so that means that the forward reaction is exothermic. Someone's just won the chasers. So if we increase the temperature, that's going to cause the equilibrium to shift to the left. So it's going to be this one, because it's going to favour the reverse endothermic reaction. And then this is one that always catches me out, but not today. Kc. Now remember, the only thing that changes Kc is temperature. So we will experience an effect. If it had been changing the concentration of something or the pressure, then Kc would have remained exactly the same. But temperature is the one thing which does change it. Now, if it's going to change, then obviously it can't be this one. It's going to have to be that it decreases. And a quick way of checking that again is Kc, remember, is the concentration of the products over the concentration of the reactants. So if it shifts to the left, the concentration of the reactants increases, concentration of the product decreases. So smaller number on the bottom, bigger number on the top, that's going to get smaller. So it's going to be A. Which is correct for an isolated system at equilibrium. This one's a tricky one to explain, and it's one where I've kind of like said, you just want to learn it really. So this is where sort of remember in equilibrium, that's where you're at your maximum entropy kind of thing. So you've got the sort of this number of reactants and products, so this very sort of complex sort of disordered system. So we want maximum entropy, and then the Gibbs free energy is then at the absolute opposite. So this is where the Gibbs energy is at a minimum. So you just want to remember it, because you just want to be sort of thinking, okay, I know this one. You won't be asked to explain it. It's just you need to know that, and it's an easy mark if it comes up then. 26, which is a conjugate Lowry acid-base pair. So remember, Lowry base pair, there's literally a proton difference between them. So it's obviously not this one or this one, because, well, there's a carbon difference between these. This one here, H2O and H3O plus, that looks about right to me, because yeah, this one has basically got a H plus more than this one does, and again, this one can't be right. So there is literally a proton difference between them. Aqueous solutions of a weak acid and a strong acid of equal concentration are compared. Which statements are correct? The weak acid is less dissociated than the strong acid. Well, yeah, that's true, because it's only partially dissociates. The strong acid reacts with a metal oxide, but the weak acid does not. I wouldn't say necessarily, although we might sort of need to heat it up a little bit more. So, yeah, I'm going to go with no. And then the strong acid has greater conductivity than the weak acid. Well, that is true, because so like it's fully dissociated, so it's going to have lots of ions present. So I'm going to go with 1 and 3. However, I'm a little concerned the fact that if there was a metal carbonate or metal hydroxide, I wouldn't have any issue at all, kind of thing, because they do tend to react quickly. But metal oxides can be a bit sluggish. However, if you heated it, it would react. So I'm gonna stick with 1 and 3 only. 28, the diagram represents the bond in aluminium chloride. So what have we got going on here? So remember, these are coordinate bonds where sort of AlCl3 basically dimerizes, so that then aluminium is a bay in the octet rule, and that's why sometimes AlCl3 is written as Al2Cl6, that you actually kind of get the dimer. So what's going on here is the aluminium atoms behave as Lewis acids. Well, yeah, there will basically be an electron pairs acceptors from the chlorines, so that looks about right to me. There's certainly not being electron pair donors, because basically you've got a lone pair of electrons on the chlorine is being donated to the aluminium. One Lewis alumina, that's rubbish, and then one chlorine adds a Lewis, that's rubbish again. So yeah, this is what we're looking for. Basically, that's accepting a pair of electrons from that chlorine, and this one's accepting a pair of electrons from that chlorine, so they're Lewis acids. Okay, 29, titration curves. Again, I've never had to really teach it, so I've been getting my head a bit more on it recently, but let's have a bit of a go. So which titration curve would occur when a weak acid is added to a strong base? So we're added to a strong base, obviously we start at a high pH value, and then we are only adding a weak acid, so we're going to end up with not a particularly low pH. So I'm going to rule these out automatically, because a weak acid will not take these down. And then yeah, we don't want this nice sort of reasonable size equivalence point in there. This one is a bit nothing. It's kind of almost like a bit like a sort of a weak base with a weak acid, and that kind of like sort of just sort of sagging curve, but it's starting off a bit too pH anyway. So yeah, I'm going to be going for this one, because we've got a strong base, starts up at around about 14. I would have liked to see maybe a bit of a sharp change to begin with, and then this buffer zone coming in. However, then we have the equivalence point where it's neutralized, and then adding further acid doesn't bring the pH down hugely, because it's only a weak acid. So it ends up at around about pH 3 to 4. So we'll go with B, remember to circle it this time. Applying IUPAC rules, what is the name of manganese dioxide? Well, we're not going to call it manganese dioxide because we don't want that, so oxide is always O2 minus. The fact there's two of them and just the one manganese, the manganese must be in a +4 oxidation state, so it's going to be manganese 4 oxide, because it's Mn, not Mg. That's the next bit done.